Today, the name of the game is hyperbolas. The goals: we want to graph a hyperbola given its equation. That's goal number 1. Goal number 2, to find the vertices, foci, asymptotes, and eccentricity of a given hyperbola. And goal number 3, to find the equation of a hyperbola given certain information about it. So let's get started. So the actual definition that we use of a hyperbola, it looks a lot like the definition of an ellipse. A hyperbola is the set of all points in the plane, the difference between whose distances from two fixed points called foci, that difference is a constant. So let's talk about the standard equation of hyperbolas centered at 0, 0. There's two standard equations. The two equations, the first equation, one version goes like this: x squared over a squared, and then minus y squared over b squared equals 1. Now, which equation does this look like that we talked about just yesterday? It's similar to, it's not exactly the same. Looks like an ellipse, except instead of having a plus between the x squared term and the y squared term, there's a minus. And it changes the look of the graph considerably. Now, the reason we have to have two equations is because if you switch the role of x squared and y squared, you get something like this: y squared divided by a squared minus x squared divided by b squared equals 1. So in the second situation, y squared's the term with y squared in it is positive. So what the heck does the graph look like? Well, if the positive term involves the x squared, it actually has two branches. One branch will open to the left. It'll kind of look like a sideways parabola, but that's not what it is. It's not the same shape as a parabola. And one branch will open to the right. So it'll have two branches. One graph will have two branches. And the center 0, 0 is right here in the middle. If the term involving y squared comes first, then you're going to get a branch that opens up, and one branch that looks like the reflection of the first branch that opens down. They do look like parabolas, but they're not parabolas. The center would be right here in this case, 0, 0. Okay, so is this easy enough to remember? If the x squared is positive, it opens horizontally. What does x control? Horizontal positions, right? So it opens left and right if the x squared term is positive. It opens up and down it opens if the y squared term is positive. Y controls the vertical, right? So that's a way you can remember it. In just a minute, I'm going to show you how to graph this hyperbola by hand. But first, let's do it on Desmos. So I'm going to type in x squared divided by 4 minus y squared divided by 16 equals 1. And you get a hyperbola. One branch opens to the right, one branch opens to the left, and the center is at the origin at 0, 0. Now I want to look at what happens when we zoom out on this thing. So zoom out, notice what's happening. It's starting to look like two crisscross lines. The two branches are starting to look like two crisscross lines. We can't even tell that they don't cross at the origin. So what's going on here? Why is the zoomed out version of the graph of the hyperbola indistinguishable from two crisscrossed lines? Well, it turns out that every hyperbola has two asymptotes associated with it. Remember, an asymptote is a line that the graph of a curve gets closer and closer to, but doesn't actually intersect, at least not the asymptotes we've looked at. So what happens is we're zoomed out so far on this hyperbola that it's indistinguishable from the two asymptotes associated with it. So we can actually use the graph of the hyperbola to estimate the asymptotes. And if I did that, if I considered like this guy one line going through the origin, even though we know that's not really what it is, that's what the asymptote is, I could find its equation. Look, this point right here, it's going by 100s on the x-axis, so you'd go 100. It's going by 50s on the x-axis. So you'd go 50, 100. It has x-coordinate 100 and y-coordinate 200. And the asymptote does, in fact, go through the origin, unlike the hyperbola. So we could call the slope of this line that increases from left to right, the rise would be 200. The rise would be 200. The run would be 100. So the slope of this line from left to right, that increases from left to right, that is 200 over 100, which is 2. If you do the same analysis for this thing that looks like a line from that decreases from left to right, turns out that will have the opposite slope, -2. And look, I want you to look at something here. If you think about the standard form of the hyperbola that I showed you just a little bit ago, this is what we would call b squared, and this is what we would call a squared. And it turns out if you think about the square root of 16, which is b, turns out b is 4, and the square root of 4, the square root of a squared is a, and that's going to be just 2. And if you look at b over a, b divided by a, that's 4 over 2, or just 2. And that's no coincidence. It turns out that for any hyperbola that opens horizontally, the slope of the line that increases from left to right is going to be b over a. And the slope of the line that decreases from left to right is going to be minus b over a. And so we're going to use the slopes of the asymptotes of this hyperbola to help us graph it by hand in the next example. Graph the hyperbola. So we have x squared divided by 4 minus y squared divided by 16 equals 1. Remember what the standard equation looks like in this form. It's x squared over a squared minus y squared over b squared equals 1, right? So here's the trick. This is the memory trick you use to help yourself remember how to graph this. You start out like it's an ellipse. Start out like it's an ellipse. So find the center. Well, the center in this class is going to be 0, 0. And you're going to go left and right how far? So you're going to go if this were an ellipse, if this were a plus right here, you would go left and right from the center, the square root of this number, to get to the edge of the ellipse if it were an ellipse, right? Okay, so let's go left and right 2. So let's go left and right 2. So I'll say it this way. A squared in this case is 4, which means a equals 2. I'm ignoring the plus or minus because I consider a length. So you go left and right, plus and minus 2 from the center. Okay, then you're going to go up and down how far? The square root of the number underneath y squared. So b squared is 16, which means you go up and down the square root of that number, which is 4. So up and down, 1, 2, 3, 4. 1, 2, 3, 4. Now, if this were a plus right here, you'd just draw the best oval you can and you'd be done, right? But it's not. So what I'm going to do is I'm going to draw a box. And the diagonals of this box are going to correspond exactly to those asymptotes. So if you draw the box with that has these 4 points as midpoints, so draw the box that has these 4 points as midpoints. And then draw the extended diagonals of the box. Now I am going to cheat a little bit here. I'm going to use my drawing tool for a line to draw the extended diagonals of the box. So the diagonals go from corner to corner, right? Opposite corner to opposite corner. So there's one extended diagonal. And that's going to be one asymptote. And then the other one, like so. Everybody see what I did there? Now, if it were perfect, the center where these asymptotes cross would be 0, 0. Of course, it's drawn a little bit freehand there, so it's not perfect. Okay, so then none of what I've drawn is the hyperbola so far, except for 2 points. These 2 points here and here. Those are called the vertices, plural of vertex, of the 2 branches of the hyperbola. Now, because the x squared term comes first, we know it opens left and right. We know that there's a branch that opens left. We know that there's a branch that opens right. And we know that it's going to follow these asymptotes. So all you have to do, long story short, is draw a hyperbola, one branch that opens to the left that goes through this left-hand point, this left-hand vertex. And it should look like it gets closer to the asymptote, so try not to fade away like I did a little bit there. Should look like it gets closer to the asymptote as it goes to the left. And then the other branch should look like a mirror image of it. It should look like it gets closer to the asymptote as it goes to the right. And so we don't really plot any points except for the 2 vertices in the middle of the box, the middle of the 2 opposite sides of the box, the vertical sides in this case. Okay, so the graph in blue, that graph, those 2 branches make up the one hyperbola.